Hi everyone, welcome to the second unit of our astronomy discussions. So we're going to go through the history of astronomy right now with the motivating question of early astronomy. Is the Earth round? So if you go along with the OpenStax textbook, at least the 2017 edition, this goes along with pages 42 through 75 of that. And I start you off with some objectives. After the end of this, you'll state the history and purpose of Stonehenge, Anasazi Sundagger, and also what's meant by retrograde motion and epicycles. Be able to describe really the history of a lot of our fundamental ancient astronomers, who we will discuss soon, and lots more. So I kind of continue here with a little bit of a joke. So this is a, quote, disclaimer. This presentation contains material in the shape of Earth. A spherical Earth is a theory, not a fact, regarding the shape of our planet. This material should be approached with an open mind, studied carefully, and critically considered. Raz. Now, the question is, what is this making fun of? So you might at first think that it's making fun of the flat earthers, but in fact it's not. This is an almost exact quote that used to be, and who knows, in some districts might still be, but used to be part of a disclaimer on textbooks in some states for biology, except instead of spherical Earth and shape of Earth, they were talking about evolution, which is kind of interesting being in front of a biology textbook because evolution is actually a fact, not a theory. Of course, there are many theories as to how evolution has proceeded in the past, with Darwin's theory being the most popular, but nonetheless, it is actually a scientific fact. Now, just like the shape of our planet being roughly spherical. So do you recognize this picture? So this picture is actually a large version of this actual photograph. This is Stonehenge in the southern UK. And Stonehenge was essentially a giant solar calendar. It started being built at least as early as 3100 BC, maybe as early as 3300 BC. It was certainly used as early as 3100 BC. The heel stone was probably used to mark sunrise on the summer solstice. So basically right here, and I think it's out of view in this picture. Unless it's this one right here, but I don't think so, because I would think that they would have it in a different spot. But in any case, it was used to mark sunrise on the summer solstice. And basically a giant solar calendar. Now, in spite of popular belief, which I have had the misfortune of being guilty of propagating in the past, Stonehenge was not built by the Druids. In fact, we really don't know who built Stonehenge, but the idea that Stonehenge was built by the Druids is actually one of the more popular misconceptions in astronomy. And I found it in an astronomy textbook, which is why I propagated this myth. But the Druids came long after people stopped using Stonehenge. Now, the ancient Egyptians had a somewhat complex study of early astronomy. They had a mythology with many gods, but their chief god, Ra, was the sun god. And in commemoration, they built their pyramids and obelisks to mimic the shapes of, well, light in the sky. For example, it's believed that obelisks were built to mimic the shape of sun pillars, which you'll sometimes see these particularly in the winter, right around sunrise, where rays of sun end up scattering off of somewhat rectangular, horizontally oriented ice crystals and end up giving you these nice sun pillars. Whereas the pyramids, we believe, were built, not just the Egyptian pyramids, but in many civilizations, were built to mimic the shape of the zodiacal light, which is this very, very faint glow. It's overexposed in this picture, but a very faint glow that is visible somewhat toward the east a few hours before sunrise, or somewhat toward the west a few hours after sunset on very dark nights. But it is definitely not an obvious phenomenon. You kind of have to be looking for it in order to be able to see it, but it does have kind of a pyramidal shape. Now, the ancient Egyptians also saw significance from the star Sirius. In fact, around 3000 BC, Sirius would disappear behind the sun's glow in late spring and then reappear around the summer solstice at dawn. Now keep in mind, there have been 5,000 years worth of precession of Earth's Earth's axis of rotation during this time, so that's about 1/5 of an entire cycle. So this no longer happens at these times of years, but at least during that time, the reappearance of Sirius could be used to forecast the rising and flooding of the Nile River. And of course, this was extremely important for crops because these floods deposited vast amounts of silt and other nutrients that were used for the crops. And so being able to forecast the rising and flooding of the Nile River was quite essential. So here you have the Great Pyramid, again kind of shaped like that zodiacal light. The pyramid itself, it has air shafts, one of which points toward the North Celestial Pole, which at that time was around the star Thuban, right now is around the star Polaris, but another of which was pointed toward Orion's belt. Well, guess what? Because of precession, Orion's belt is not in that part of the sky anymore, but it was back then. So interestingly, this actually gives you an independent means of getting an estimate for the age of the Great Pyramid, which is independent of, but of course in corroboration with, the estimations that you get based on radioisotope dating of that area. Native American astronomy. So not only are the constellations that we consider in the night sky a bit different according to Native American mythologies, but they also have some other achievements that are a bit different from what we normally consider as to be astronomical. For example, the Anasazi Sun Dagger. It's at the top of Fajada Butte, which is in New Mexico. So you just have this kind of tall area rising up from around the land. It's kind of hard to get up, but they found ways. But there is a particular opening in the rock crevices up there where at noon on the summer solstice, a ray of light is able to peek through. So they found where it peeked through, and they made this 19-turn spiral around it. So that way, generations henceforth would be able to determine when is noon on the summer solstice. So basically, in a manner of speaking, they created part of an astronomical calendar there. Now, what about the ancient Greeks? The ancient Greeks are going to form a major part of the rest of our discussion. The ancient Greek civilization was the greatest center of intellectual achievement in the ancient world. Now, the Greeks were conquered by the Romans, but the Romans adopted a lot of Greek discoveries. They actually held a special place in their society for Greek intellectual slaves, and they were actually put higher than your typical Roman citizens, at least if they were in the places of people like doctors and teachers and philosophers. And so you kind of wonder at the end of the day who really conquered who. It's like, yeah, okay, the Greeks militarily were conquered by the Romans, but it was Greek civilization that ended up taking over the Roman Empire in many manners of speaking. So the ancient Greek philosophers created some of the most important achievements in the history of science and mathematics. So we're going to examine some of those now. Thales of Miletus, he lived between 624 and 546 BC. In Anatolia, which is now part of Turkey, but that was part of the Greek Empire. But he put forth this idea that views of reality should be based on repeated observations of nature instead of supernatural and mythological explanations. In other words, he was an observational scientist, which is one of the main types of science out there going by the scientific method. And then there's Pythagoras, who has given many generations of mathematics students nightmares with his, or at least his followers' theorem about relating the sides and diagonal of a right triangle. And he and his followers believed that each sphere carried one of the planets, our moon and our sun, and that another sphere carried the stars. And they thought of spheres because circles and spheres were seen as the ideal creations. So here you have Earth at the center, surrounded by a sphere containing moon, and then Mercury, Venus, Sun, Mars, Jupiter, and Saturn. So, and they did get the kind of the order to some extent right. But other than that, the idea of Earth being at the center, yeah, that's going to plague us for a while, as you're going to see soon. Now, the Pythagoreans also understood that the curved shape of the terminator, that is the day-night line between light side and dark side of the moon, throughout all of its phases, throughout all times of year, proved that our moon must be spherical. So if our moon must be spherical, it seemed reasonable, at least, that Earth would be spherical. Now, we'll have more to say on that soon. What about Plato? This is Plato, not Pluto, but Plato. In his philosophy, the idea was that the material world that we observe is an imperfect representation of the ideal creation. So he believed that you can actually learn more by reason than by observation. In other words, Plato and his followers were theorists. They believed that you get a better understanding by using reason to figure out what is actually going on. Well, theoretical scientists are the other big major component of the scientists out there. So basically you have observers, and then you have theoreticians. So observers / experimentalists and theoreticians. Now, one of Plato's students, Eudoxus, developed a model of the cosmos where Earth is surrounded by 27 spheres, but it was clear that Eudoxus considered these to be a model as opposed to a physical reality. Now, on to Aristotle. Aristotle was a student of Plato. He was also the tutor of a certain military leader named Alexander the Great, and Aristotle knew that the sun is more distant than the moon. And he noticed that during a total solar eclipse, the moon passes between Earth and sun. So that was one of his big ideas. Yep, the sun is definitely more distant than the moon, so the sun must be larger. Now, he also, in fact, even before him, people noticed that during total lunar eclipses, you always had a curved shadow falling on the moon, and that demonstrated that Earth was spherical. And comparing Earth and Sun, that also allowed people to predict total solar eclipses as well, because by understanding that Earth is spherical and that the moon is spherical and is going to always cast a circular shadow. Now, Aristotle took this a step further, though. I mean, before that, yeah, people knew that Earth was spherical, but Aristotle actually came up with an understanding of why Earth is spherical. So first of all, just some observations that could be noted at that time and that he noted. He noted that as you travel north, the stars near the north celestial pole are higher in the sky. Well, that's not going to be the case with a flat Earth. As you travel south, stars that never rise above the horizon at northern latitudes, suddenly they become visible. In other words, there are stars that you can see farther south that you can't see farther north because they're hidden by the horizon. Well, again, that's only going to be the case if the surface is curved. And also, during a lunar eclipse, the shadow of Earth is always round, as we just mentioned. So there it is again. We saw this back in the previous unit. So again, he presented a theoretical argument to come up with an idea of why Earth is spherical. So in other words, remember the big point about scientific theories. Scientific theories don't just state beliefs like theories in everyday language. Scientific theories put forth an explanation as to why things are the way they are. So Aristotle's theory of a spherical Earth was that the reason that a spherical Earth was a fact was because material falling toward a common center would take on a spherical shape. So this was Aristotle's theory as to why Earth is a sphere. In fact, his theory is true. We now recognize that what we used to consider a theoretical argument actually is the reason why Earth and the other planets are spheres. In fact, it has even greater importance when we speak about dwarf planets later in the course. Dwarf planets, the difference between a dwarf planet and something that's not big enough to be called a dwarf planet is that a dwarf planet has enough mass to round itself into a spherical shape, whereas something that's just like, say, oh, just an asteroid or just another Kuiper Belt object won't necessarily have enough mass to round itself into a spherical shape. That's what makes dwarf planets more special than other things like asteroids and other Kuiper Belt objects and stuff like that. So Aristotle believed that there's a fundamental series of natural laws that describes the behavior of objects in the universe, and that we can figure these out through observation. In other words, Aristotle kind of put together theory and observation into a whole big scientific method cycle, kind of a dual cycle in a way. So this is now really how modern astronomers, and for that matter modern scientists, develop scientific models. So Aristotle, though, he had other beliefs. He believed that all objects are created from 4 simple elements: earth, water, air, and fire. And he believed that these were all part of something kind of bigger in the heavens called the ether. So in other words, a periodic table quiz in chemistry class during Aristotle's time would have been incredibly easy. As long as you remember the basic 4 and then the 5th, you're fine. You'll be good to go for the year, at least on the periodic table quizzes. Now, in addition, Aristotle believed that the natural state of an object was to be at rest. This was simply a belief based on observation. He didn't understand that the reason that moving things come to a rest is because of something called friction. That was something that wasn't understood until many centuries later, but it was eventually understood. But Aristotle believed that based on observation, the natural state of motion for an object is to be at rest. And he called this the horse cart theory. In other words, a horse is required, or at least we call it the horse cart theory, because he noted that a horse is always required in order to move a cart. Take away the horse, the cart doesn't move. Now, Aristotle actually believed that Pythagoras' spheres were a physical reality, and thus that the universe, since the stars were on the outer sphere, was finite in extent. Now, he was apparently aware that the daily motion of the sky could be explained by the rotation of Earth, or, equally well, by the rotation of the celestial sphere around Earth. He also apparently considered the possibility that Earth revolves around the Sun, but he rejected this on observational grounds, because if Earth did revolve around the Sun, then some stars would appear to move back and forth over the course of a year based on our different perspective view. In other words, I guess he considered different stars to be on different outer spheres, with the brighter ones being on closer spheres. And the fact that this observational parallax, this shifting of the closer stars with respect to the rest of the stars, was not observed, meant that Earth is not moving. In other words, he wasn't so naive to say, oh, Earth must be at rest. As far as we can tell, he considered that possibility and rejected it on observational grounds. So, of course, now we recognize that Earth does rotate, and that's the reason that we see the stars move through the sky over the course of a night, and the sun and moon move through the sky over the course of a day. So we've discussed this parallax before. The closer the object, the larger the shift will be, because you're going to be viewing it at different angles with respect to background objects. But as it turns out, the stars are just too far away, which we'll get to soon. Now, ancient Greek astronomers Aristotle and Hipparchus believed that Earth could not be revolving around the Sun because they couldn't detect parallax. Even Tycho Brahe, who was the greatest of the pre-telescope observers, was not able to detect parallax. So he also, many, many centuries later, concluded that the stars are not moving. In fact, concluded that Earth is not moving. In fact, we didn't discover parallax until at least the 1820s, and really it's not well established until the 1830s with the observations of Bessel. So he's often credited as the first person to measure the parallax, where he found in 1838 that the star 61 Cygni is 10.3 light years away. Though now we recognize the distance, that his derived distance was off by a little bit. Now, Aristarchus of Samos was the first astronomer, as far as we can tell, who actually put forth the idea and believed it that Earth was going around the sun. Now, he was famous for other reasons. He determined the size of the moon and the sun and the distance to the sun through an exercise in geometry. Now, he was wrong, but he still recognized that the sun's about 7 times the diameter of Earth. Turns out it's much larger than that, and that it's 19 times as far away from the moon. Well, since he was wrong by a factor of, let's see, I guess that's a factor of 15.5, then it would be expected that he would be off by a similarly large factor for how far away the sun is compared with the moon, which turned out he was off by over 15.5 on that. He was off by over 20, in fact. Now, the reason that he was off so much is because of the fact that, in truth, moon is going around Earth, and the fact that there is that motion makes it difficult to make these types of determinations. Now, Aristarchus, though, since he noted that the sun must be much larger than Earth, even in his small estimation, this led Aristarchus to propose that, well, it would be appropriate for the largest object to be at the center of our solar system, or, well, the universe was what they considered it then. So this led Aristarchus to propose that the sun was at the center. And he concluded, based on this, that the reason there is no parallax in the observation of the brightest stars, which ancient astronomers believed to be the closest ones, they were mostly wrong on that, was because they were incredibly far away. Well, his detractors said, well, they can't be that far away. If they're that far away, those distances would have to be astronomical. Well, of course, it turns out they are. Now, Aristarchus had actually built on some work by a guy named Heraclides, who proposed that Earth rotates, and that is the correct explanation for the motion of the stars through the sky and the motion of moon and Earth and the sun through the sky. He also proposed that Mercury and Venus, since we never observe them being very far from the sun, must actually revolve around the sun and not around Earth. But Heraclides said, yeah, but after that, everything revolves around Earth. The outer planets, Mars, Jupiter, Saturn, they're going around Earth, and the sun is going around Earth as well. And of course, the moon is. Yeah, that's one thing that the ancient astronomers all got right. They all agreed that Earth is being orbited by the moon. So they got that part right. But Aristarchus extended the ideas of Heraclides into the overall heliocentric system. Heliocentric means sun-centered. Geocentric means Earth-centered. Okay, so next we're going to turn our attention to Eratosthenes. He was one of the most remarkable of the ancient astronomers. So he actually made the first accurate determination of the size of the spherical Earth. So he used the fact that the sun is so far away, which had been demonstrated by previous astronomers, as we mentioned before, to note that the light rays are essentially going to be parallel when they arrive here on Earth. Now, he noticed that at Siene, Egypt, which is now the place we call Aswan, where they have the Aswan High Dam for the Nile River, sunlight fell to the bottom of a deep well on the first day of summer at noon. In other words, Siene is on or around the Tropic of Cancer. But at the corresponding day and time in Alexandria, which was 5,000 stadia, we'll get to that unit soon, north of Siene, or Aswan, he observed that the sun made a 7-degree angle south of the zenith. In other words, a shadow would fall such that its length would correspond to a triangle where you have an angle of 7 degrees from the vertical for the sunlight. So because of that, he realized that Alexandria must be 7 degrees north of Aswan. Now, he knew about trigonometry because, after all, the ancient Greeks invented trigonometry, and based on that, realized that 7 degrees must be 7 360ths of a circle. So that's about 1/50th of the circle. So Eratosthenes was able to estimate that the circumference of Earth was about 250,000 stadia. In other words, he took his 5,000 stadia between Aswan and Alexandria and multiplied by 50. and then saying, okay, diameter of Earth is going to be the circumference divided by pi, he was able to determine this. Now, what's a stadia? Well, using the most common stadium size, which is probably what he would have used, because it was a unit of length there, which being about 1/6 of a kilometer, his figure turned out to be within 1% of the correct value of Earth's circumference. In other words, Eratosthenes, just using trigonometry, was able to determine the size of a spherical Earth to within 1% of the correct value. So yeah, not only did the ancient Egyptians prove that Earth was spherical, or sorry, not the ancient Egyptians, but ancient astronomers, the ancient Greeks, Egyptians, etc., proved that Earth was spherical, but they actually knew the right size. So what about the Columbus myth? So back in elementary school, you might have come across some history book that incorrectly states that Columbus had trouble getting funding for a voyage from Spain to India going west because he was not able to convince people of the roundness of Earth. That is a complete fabrication. And then some other people might come across and say, oh, that knowledge was lost during the Dark Ages. No, that knowledge was not lost during the Dark Ages. That knowledge survived just as it survives to us from ancient times. So the ancient Greeks knew and proved that Earth was round, and that knowledge lasted. Here's the thing. What happened was that Columbus had consulted a mathematician in his time who was using questionable math. The mathematician convinced Columbus that Earth was a lot smaller than the estimate given by Eratosthenes and others. So the debate wasn't about Earth's shape, it was about Earth's size. Columbus thought that Earth was much smaller than it actually was. And since distances across land were known, but distances west across the ocean were not known, this led Columbus to believe that the size of the ocean between the western part of Europe and the eastern part of Asia must be relatively small. So he could just cut west and end up getting to Asia relatively quickly. Well, as it turned out, there was his voyage would have completely failed. Everybody would have died if it wasn't for the fact that there was a forgotten continent that the Scandinavians had discovered, and that information had been lost to at least a lot of the rest of Europe. But yeah, it was lucky that that continent was there, of course, that continent being the Americas. Now, by the way, the myth of the Columbus flat earth thing, that was actually from a fictional work by Washington Irving, and that was cited by a historian who really wasn't very good, named Andrew Dixon White. Now, what about Hipparchus? We've actually mentioned Hipparchus before. Hipparchus was the greatest of the Greek scientists and astronomers. In addition to what he did in astronomy, he was also a great geographer as well, and also good in a lot of other sciences. So he invented the latitude and longitude system that we use for Earth today. He also invented the magnitude system, as we noted before. He was the inventor of the magnitude system. He's also the person who discovered the precession of Earth's axis. Of course, he didn't think that it was about Earth's axis, but he noted that there was this precession of the stars when he compared different texts of ancient stellar catalogs with what was observed during his time. Unfortunately, none of his original writings exist. We simply know about him because of other ancient authors whose writings did survive. The burning of the Great Library at Alexandria resulted in the loss of a whole lot of ancient works. So that's actually one of the biggest tragedies of the ancient world, along with another tragedy of similar nature that we're going to mention soon. So, depiction of Hipparchus. He built an observatory on the island of Rhodes. As we mentioned, he invented a magnitude system and compiled a star catalog of about 850 entries, and noted that these positions were a little bit off. He noted that shift happens, which was basically the early discovery of precession. He also obtained very accurate distances to the moon. He determined that the distance to the moon is about 59 times Earth's radius, so he was off by less than 2% on that. He determined the correct length of the year to within 6 minutes, and he tried but could not detect parallax of stars. So he concluded that Earth must be at the center of the universe, because if Earth was moving, you should expect to see parallax. So he devised a system using uniform circular motions that could account for the position of sun and moon. In fact, he introduced the system of epicycles and deferents that we're about to discuss soon when we discuss Ptolemy. And he was able to use this system to predict the positions of sun and Earth and moon for future dates, and could predict eclipses to within an hour. That's pretty important, because remember, during ancient times, especially with people being both combination of religious and superstitious, they believed that these types of eclipses portended certain major events, like the falls or rises of kingdoms and dynasties and stuff like that. But again, unfortunately, none of his writings survive. But Ptolemy knew about him, and it is Claudius Ptolemaeus, not Ptolemy, but he lived around 140 AD, and he compiled a series of 13 volumes known as the Almagest, or Almagest. It's our main source of information about Greek astronomy. Now, he developed a geocentric model that was so useful and successful in predicting the positions of the planets that it endured for more than 1,300 years. Now, a fundamental question, you could say, in astronomy is, why do the planets appear to move through the night sky? Of course, nowadays we recognize that it's a combination of the planet's motion around the sun and Earth's motion around the sun. But this was a fundamental question for ancient astronomers. Why do the planets move around in the night sky with respect to the background stars? If you watch Mars or Jupiter or Venus over the course of many nights, you will notice that they move with respect to the background stars. They don't stay in the same spot, and they have different types of motions. In fact, if you watch them over a long enough period of time, you will notice some retrograde motion. So, the way to explain this is first by looking at what is really causing retrograde motion. So let's say you have an outer planet, in this case Mars, or maybe Jupiter, I don't know, but some outer planet, and look at it from the point of view of Earth. So, as Earth goes around the sun, well, Earth is not only going around on a smaller circle, so it's able to complete more loops in the same amount of time than a planet going around on a larger circle at the same speed, but it's also going around faster because it's closer to where the sun's gravitational influence is. Stronger force means that you're going to have a larger acceleration, which for circular motion in this case means a higher speed. So as Earth goes around the sun, well, as it catches up to Mars, Mars appears to go backward with respect to the background stars. And that will last as long as Earth is in the process kind of passing Mars until it gets far enough ahead that it's kind of starting to loop back on the other side of the circle. So as Earth is catching up to Mars, here we have the view of Mars with respect to these background stars at point A. But then at point B, Mars is kind of up here. That's kind of the normal motion. That's what we call prograde motion. But then at some point, it seems to cease its motion with respect to the background stars and then move backward. That moving backward is what we call retrograde motion. This is retrograde motion. It's moving backward in this sense. And that's what's happening as Earth is passing Mars. The same thing happens if you are on a track. If you're on the inner lane of a track where you're supposedly going faster than the people on the outer lanes, when you pass them, they are going to appear to be going backward with respect to the background grass, hills, mountains, or whatever. Until you get far enough past them that then what you're seeing is they're just kind of undergoing their normal motion with respect to the background. Until you get up to passing them again, and then they kind of start to appear to go backward with respect to the background. Same thing with retrograde motion, the real reason why it's going on. Now, how did the ancient people explain this? Let's take a look. The way that ancient people explained this is they believed that a planet does not go around Earth in a perfect circle. Instead, it goes in a circle that itself is on top of a circle. So it's kind of like the teacup rides at Walt Disney World and similar types of rides where you have a set of seats that are moving in a circle that itself is placed on an arm that revolves around. So basically we have this little circle where the planet is actually moving is what we call an epicycle. Now, in the original model before Ptolemy, the epicycle was placed with its center on something called a deferent, which itself was centered on Earth. The deferent was the big circle, and the epicycle would move on the little circle. But as the object was on the epicycle, it was moving around on the epicycle. So it's like it would end up kind of creating a spiral pattern as it went around. So you'd have kind of a spiral pattern, and when it's going backward, right here, there's retrograde motion, prograde, retrograde, prograde, retrograde, prograde, retrograde, etc. So that was their explanation of the retrograde motion that planets undergo from our point of view. Now, Ptolemy made a series of adjustments to these epicycles. He noted that just using circles, perfect circles with their centers on top of other perfect circles that were centered on Earth, did not produce very nice agreement with observations. It produced some agreement. It explained the retrograde motion, but it wasn't able to get to the finer points. So Ptolemy did a couple of things. First, he wouldn't necessarily have the center of an epicycle on the center of a deferent. Second, he didn't have Earth at the center of a deferent. Instead, Earth would be off-center, and at an equal distance off-center was another point called the equant point. And the idea is that a line going from the equant to the center of the epicycle would basically go around at constant angular velocity. So a result would be that as the planet was closer to Earth, which would mean a longer arm but going at the same angular velocity, the planet would go through the sky faster. And when it was farther from Earth, you'd have a shorter arm but going at the same angular velocity, it would be going around slower. And since it was farther from Earth, you would see it move slower as well. This is actually relatively close to what geometric figure? Give you a chance to think of it. This is relatively close to an ellipse, where an ellipse will have two focal points. It's just that Ptolemy's still stuck with circles for the deferents. But imagine if Ptolemy had come up with ellipses. I mean, it would have been incredible, because another one of Ptolemy's improvements was instead of just having one epicycle on top of a deferent, he would have epicycles on top of epicycles to explain some of the finer motions of the objects in the sky, the planets, the so-called wandering stars. And in so doing, he was able to get really close to the true approximation. Now, as we're going to discuss later on, Kepler showed that the motions of planets around can best be explained by going around the sun in paths of ellipses. But imagine if Ptolemy had come up with ellipses here and had Earth at one focal point of an ellipse and the equant point at another focal point of an ellipse. Ptolemy's model would have been incredibly accurate, and it probably would have challenged scientists for even longer to come up with the correct explanation because of the fact that this model turned out to be so accurate. So, as we mentioned, the deferents came before, but Ptolemy had improved this cycle by using the equant points and also putting epicycles on top of epicycles, or at least using those combined with the equant points. So, again, this whole idea with the equants going at constant line from the equant to the center of the epicycle going at constant angular velocity, this actually made a very good approximation for the observed motions of the planets in the night sky. They weren't perfect, but nobody could come up with anything better. So again, the correct explanation for the retrograde motion is the fact that when we're in the process of passing a planet, a superior planet, we observe that planet going backward. Or when an inferior planet is passing us, we observe that as having a different motion compared with how we would normally see it move. In other words, that would be its retrograde motion from our point of view. What about other cultures? We've spent a lot of time talking about the ancient Greeks. A lot of that is because of the fact that Greek civilization got so widespread throughout Europe and a lot of the rest of the world because of the Roman Empire. Their scientific discoveries became well known because of being spread out through the various texts and the teachings of the Greek intellectuals to the Roman intellectuals, etc. But there were other ancient astronomers out there. For example, the ancient Chinese astronomers. Now, as you may know, ancient China at times had quite a large empire. Sometimes, I mean, it was never as large as the current country of China, but at times it was still quite large. So you might wonder, why didn't those teachings from that time end up getting saved? In fact, as it turns out, around the 700s or 800s BC, ancient Chinese observers were describing comets. And they were doing that in some detail. And if they were doing that, you can probably figure that they were doing a lot of other things. But unfortunately, when the founder of the Qin dynasty, Qin Shi Huang, came into power, he ordered that all of the ancient texts be destroyed, and that anybody who was found with any of those would end up getting burned alive. So as a result, a whole lot of that was destroyed. Basically, he wanted to completely annihilate any knowledge of previous dynasties and say that, hey, the real founding of China is right now as opposed to sometimes before. Kind of reminds you of October 1st, 1949, where Mao Zedong kind of did something very similar. In fact, they call that New China, and that still that day is celebrated every year. But in any case, with this burning of and other destruction of the ancient texts, we've lost a whole lot of our knowledge about what happened in ancient China before about the year 200 BC. Of course, not all of the stuff was destroyed. Some people risked they and their families' lives by hiding some of these things away, and as a result, we do have some of this knowledge. But unfortunately, most of it was lost. But we do know that they were observing comets around 700 to 800 BC. They were probably doing a lot before that. They were observing and describing sunspots 2,500 years ago, so that was also before the time of Qin Shi Huang. And they also, afterward, just observed the first and described the first recorded supernova in the year 185. Now, Indian, Arab, and Egyptian astronomers also had important contributions. Interestingly enough, in one of the Vedic texts in Hindu scriptures, they have a statement concerning the speed of light that turned out to be correct to within an order of magnitude of the actual value. Now, an order of magnitude, like a factor of a few or so, might not seem all that great, but when you consider the fact that it had been believed that the speed of light was infinite, to get it right to within the right order of magnitude is quite remarkable. Now, they might have just been lucky on that. In other words, you might say, well, there were so many ancient traditions that somebody was bound to get it right. That might be true, but nonetheless, we can kind of pin it on what was already, what we know to have already been a highly intellectual society. The ancient Mayans were also astronomers. As you may have heard, they had their Mayan calendar and everything that supposedly ended in the year 2012, so the world should have ended at that time. But given that I'm giving this lecture 8 years later, that's not when the world ended. Of course, some might say that the world is in the process of ending in 2020. But in any case, it didn't end in 2012, and it shouldn't have either. The predictions that they made with their calendar weren't always necessarily favorable, or at least favorable in terms of being found correct by observation and experience, but nonetheless, they were quite successful in terms of a lot of their astronomical observations, as were quite a number of other cultures. So that is it for our discussion of the ancient astronomers. Next time we will discuss some of the more recent figures in astronomy from the time of the Renaissance, starting with people like Copernicus. So I'll see you all then, and thank you for watching.